We're going to start with a very simple example. The example is just dropping a ball and letting it speed up. Now you've noticed that I've got some buckets up there. And that's because energy is a scalar. Ooh, what does that mean? A scalar means it's not a vector. You don't have energy to the right or energy to the left or energy to the east or energy to the north. They're just energy. You got it or you don't got it. It's like money. Old guys got it. Young people don't. Okay? And like money or like paint that you either got or don't got, you can put it in a bucket. So I'm going to define a kinetic energy bucket. I'm going to define a gravitational potential energy bucket. And then I'm going to define a bucket that is the sum of those two. Now that third bucket we sometimes call total energy. Sometimes we call it mechanical energy. Its proper name is total mechanical energy. But we're going to be fairly sloppy. We're just going to call it total energy for the most part. Okay? Now, let's look at that first bucket, the kinetic energy bucket. This is the formula that fills that bucket. Trust me. Why would I lie? Okay? Now let me see if I can motivate it. Remember, energy is the capacity to do damage. When my daughter, bless her heart, was a teenager, I taught her how to drive in a 1979 Chrysler Cordova with rich Corinthian leather. Those of you that are not familiar with this car, it's a land yacht. The hood goes on forever. It's like a tank. And so my daughter was going around town with a large capacity to do damage. And we had a lot of problems with our insurance. But this wasn't the problem. This was. It turns out that my daughter only knew one way to drive that big old tank, and that was pedal to the metal. And that speed, that V, is squared. That means you're going twice as fast. There's 4 times the capacity to do damage. 3 times as fast, 3 times the capacity to do damage. I shouldn't share this. She's a wonderful, wonderful person. She's got 4 lovely children. One of the smartest people I know, a biologist. Excellent person. But I got to tell you this story. The church parking lot is empty except for 2 cars. Okay? My car and the person that I'm in the church talking to. And the next thing I know, my daughter's at the door knocking, and she said, "Dad, could you come out here? So just tell me." No, come out here. She had been trying to teach her friend how to parallel park using this other guy's car as a prop. And during the process, she had completely taken out the side of his car. And I had to go back in and tell him that his car was totaled. Another time, I'm giving a lecture. I look up, and there are my 2 oldest children in the back. Just came to lecture. And so I was so proud that they would use their day off. It was a PIR day, and they used their day off to come to my lecture. I was just so touched. And so I involved them in the demos and everything, and it was a wonderful lecture. At the end, I said, "How did you like it?" "Oh, Dad, we've got to talk." "What about it?" "Oh, Dad, we were on our way to a party, and Heidi was driving, and she sideswiped this car right near campus. We came to find you, but you were already teaching this lecture, so we had to sit through the whole thing." That is so crushed. Anyway, 1/2 mv squared. Memorize it. Those stories won't be on the exam. Okay, if we take m to be 1 kilogram, and it's not moving initially, then there's nothing in that bucket. Let's look at the second bucket, this gravitational bucket. Now, the formula for that bucket is mgh. Take my word for it. Now let me see if I can motivate that. If I remind you that energy is the capacity to do damage, whoa. Worried?
Yeah, a little bit.
A little bit. And he would be more worried if this were an anvil, okay? And he would be more worried if the anvil was higher above his head. Now, we've dealt with this. The bigger the mass, the more worried he'd be. The higher it is above his head, the more worried. What about that one there? Why is that in the equation?
Acceleration due to gravity.
Yeah. And what if we were on the moon? If I had that up above his head and I dropped it on the moon, would he be as afraid? No, because it would just gently float down. The acceleration due to gravity is 1/6 as strong on the moon as it is here. And so all of those things tell me how afraid I should be of something over my head. Now, I know that this is 1 kilogram for the ball. G is 9.8, we're going to call it 10 newtons for each kilogram. It's this H that we need to deal with. And that H requires a coordinate system. Now, when you wake up in the morning, you have a right to choose your own coordinate system. But there are some coordinate systems that are easier to use than others. If you always use the lowest point in your problem as your zero of height, you will never have negative height. And that'll simplify your problems. So I'm going to set up a coordinate system where that ball starts at 5 meters above the floor. And that's going to give me 10 times 5 or 50 units of energy. Does anyone know what the units of energy are? Joules, yes, joules, because energy is so valuable. Is that right?
No.
Maybe not? No, actually it's joules. We defined that unit to honor a dead professor, one of the best things you can do with your life. And let me put that one up here. Potential energy, gravitational, MGH. So we would have 50 joules of potential energy, and hence 50 joules of total energy. And then I drop the ball. Now once it gets down 1 meter, I look again and see how much are in each of the buckets. Now to figure out how much is in the kinetic energy bucket, I need to know how fast that ball is traveling. You've been able to solve that since the second week of class. We define a coordinate system. Let's call down the positive y direction. We set up our 5 players. My delta y in this coordinate system is a +1 meter. It starts from rest. The acceleration in this coordinate system is positive because it's down. I'm looking for v final after it's dropped 1 meter. Time is the one that I don't care about. That suggests I should use the equation that doesn't have time. I plug into it, and what I get is that. If delta y is equal to 1 meter, that gives me the square root of 20, which is 4.5. So let's fill up our buckets. The kinetic energy bucket is going to be 1/2 times 1 times the square root of 20 squared, and that's going to give me 10 units of kinetic energy. My potential energy, my height is only 4 meters now, so I now have 40 units, or 40 joules. And behold, that's what conservation means. When we say energy is conserved, what we mean is total mechanical energy is conserved, stays the same. Okay? Now, anytime something's conserved, you can use that. Those are some of the most powerful principles of physics, or places where something is conserved or stays the same. Now let's let that ball drop another meter. Okay? Its speed is going to be the square root of 40, or 6.3. Okay? Well, let's see if that works out. Well, I know that the potential energy is 30 units, because it's 3 meters high. If that total energy stays 50, that means I must have 20 units of kinetic energy. Well, let's check. If I plug in, sure enough, I get 20. Now, what this gives me is a new way to answer this question. How fast will the ball be traveling when it's 1 meter from the ground? Well, I say the total energy still has to be 50 joules. That's what I started with. The gravitational energy when it's 1 meter above the ground is only 10 joules. That means I must have 40 joules in that kinetic energy bucket. If I know how much kinetic energy I have, and I know the mass of the ball, I can find the speed. I just plug and chug. What I get is 8.9. Now I think I know what you're thinking right now. You're thinking, Greg, you just gave me a second way to solve a problem I didn't care about. I didn't care how fast that ball was going when it was 1 meter above the ground. I had to learn the first way to get through the first exam, and now you're teaching me a second way. Why don't I just use the first way? Well, it turns out that there are some problems that you cannot solve using the kinematic equations, and energy will allow us to solve those problems. There are other problems that you can solve both ways, with the kinematic equations or with energy. And in each of those cases, energy is going to be the easier way to go. Now folks, I swear, got a building full of physicists. Well, there's some engineers on the third floor, but we ignore them. All these physicists, if they get a brand new problem they've never seen before, the first thing they try, the first thing they use is energy. Because if they can use energy to solve the problem, it's going to be easy. It's going to be easy.